Okay. Yeah, thank you for inviting me and giving me the opportunity to present a recent paper of us, actually, which was written also with together with Felix Kaack, who just spoke, and Priya Danti, who will be speaking later. And this paper is entitled Aligning Artificial Intelligence with Climate Change Mitigation. And it's particularly addressing some of the impact assessment questions around machine learning. So some of what just came up already in the discussion, and how and what we can do to shape the overall impact of machine learning. So I wanted to start with a little bit the background story for this paper. So some of us, including Priya and Felix, wrote a very long paper a couple of years ago titled Tackling Climate Change with Machine Learning, where we illustrated how machine learning can be used to address climate change. At the same time, Emma Strobel and her colleagues wrote a paper that for the first time really illustrated how large the computing footprint can be of developing certain deep learning models. And both of these papers got quite a lot of traction, and they also got portrayed in the media as really like two opposing stories almost. So one is saying, okay, AI is really good for the climate, and the other story is it's bad because of the very, very large computing footprint. And to just illustrate this, within 2 weeks, MIT Technology Review covered our paper, telling the story of how good it is for fighting climate change, and telling the opposite story of how many emissions or how much emissions comes from machine learning. And actually, these articles were even written by the same author, Karen Howe. So this story like stayed in the public mind for quite a long time, and what we wanted to show is that it's not really is it good or is it bad, but it's really two sides of the same coin, and there's even a much broader, more holistic way to look at the impacts of machine learning. So that's what I'm going to talk about today. And I wanted to also say a few words why machine learning is relevant at all to look at. And I'm going to use sometimes machine learning and AI interchangeably. Machine learning is sort of a sub-technology of AI in some sense, and has been driving much of the AI progress recently. And why this is so important is that we could view AI and machine learning as a wild card that can influence our ability to decarbonize in various ways. And I brought a quote from Andrew Ng, who is a machine learning professor. And here in this quote, he compares AI to electricity, where he says that electricity about 100 years ago transformed almost everything. And now he has a hard time thinking of an industry that will not be transformed by AI. That might be a very optimistic view on the abilities of AI and machine learning. But so what it illustrates is that it can change the economy more profoundly. And I also brought a plot that shows the corporate investments globally in AI. They have certainly been rising quite a bit over the last years. So the economy is looking into deploying AI much more broadly. So in this paper, we introduce a way to think about the overall footprint associated with machine learning. And we largely divided in 3 different aspects. So we talk about the emissions that come from the machine learning computation and the hardware, because machine learning algorithms obviously run on data centers or servers, and they consume energy and they use materials for that. Then machine learning is also a multi-purpose technology, and we need to look at what kind of emissions it's causing by the way it's being used. And you can, of course, apply machine learning to address climate change, but you can also apply it in ways that might counteract that and increase emissions. And then lastly, machine learning also interacts with the larger technological, social, and economic system in ways that can, of course, help or hinder climate change mitigation. And this is what we call the system level impacts in this paper. And in this talk, I wanted to address all three of these aspects in more detail. So let's start with the emissions from computation and hardware. And this plot shows the emissions that come from training an algorithm. It shows different algorithms on the x-axis. And it shows the emissions on the y-axis. And please note that these are also on a log scale. And it compares those to different typical activities and what kind of energy, how much energy they consume. And essentially what's the message here is that emissions from training in machine learning differ significantly between the model types. And they also depend on whether a model is fine-tuned or trained. I'm going to talk more in detail what that means. But all of these are also deep learning models. So we're talking already about the much, much larger machine learning type of models. And the most energy intensive model that the study looked at is this model with 6 billion parameters that emits about as much as powering a home for a whole year, which is really a lot. On the other side, fine-tuning BERT, which is a very common language model, and is emitting less than a gallon of gasoline per training run, so much less. Here we're talking about fine-tuning, so we're not actually retraining the whole model, but we're training just some parts of it that are adapted more to our task. We're reusing sort of the model that has been trained on much larger data sets before. So generally, the size of the model also matters a lot for how much energy is consumed for training. So here are different sizes of this vision transformer model, from tiny to huge. And you can see how the energy consumption during training also increases depending on the size. And size here refers to the number of parameters that need to be trained in the model. So what the authors here measure is the operational emissions. And I wanted to talk a bit about those operational emissions and the embodied emissions and what we mean with this. So operational emissions come from the energy consumed while running the algorithm on the hardware. And of course, they depend on the energy efficiency of the data center or the server that it's being run on. And data center efficiency can be improved with more efficient hardware. And there have actually been lots of progress recently making hardware more efficient with better cooling techniques, or also by means such as using waste heat, for example, from data centers to heat homes. And then, of course, they also depend on the type of electricity being used. So if a data center runs on almost 100% renewable energy, of course, you have much less emissions associated with it. Also, data centers have a unique opportunity to help with integrating more renewables into the grid by providing a load that's actually flexible. And generally, just a note, and this might be very familiar to all of you, but one often gets the question, okay, if they run on 100% renewable energy, why is efficiency so important still? But of course, efficiency is absolutely important because you need that energy to also power a number of other things. And you can also reduce the amount of renewable energy being built out if you have energy efficiency. So you want to avoid wasteful consumption in the data centers, of course. And that brings us also to the second part, that we have embodied emissions from the hardware. So when you produce or you all the way to the end of the life of the hardware, you have emissions. And so, for example, if from mining, from production of the chips, of the hardware, from transportation until the end of life and the disposal and the recycling. And what you see in these pictures, that especially in the end of life and in the mining phase, is that there are also lots of other kinds of environmental impacts connected to the hardware. So for example, water impacts, social impacts, of toxins being released in the process. So we have also lots of other environmental impacts that one needs to look at here. Okay, so I wanted to dive a bit deeper into how we can actually go about assessing now the overall emissions from machine learning. We talked about how to assess the training of a single algorithm, and we talked about the data center perspective. But what we're really interested in is how can we associate emissions to the technology itself? And the figure here illustrates in an abstract way how we can think about this during different life cycle phases of the algorithm itself. And some of these horrendous numbers that one also sees in the media of how large the footprint is of single machine learning algorithms come often from the development phase. And development is something that's not done very often in practice. Is here you train the algorithm several thousand times to experiment with different configurations. And then of course that adds up to a huge amount of energy. Training itself, a single training run, you do more often because you need to adjust to the changing data, for example. So training is done more frequently, but something on the scales of, depending on the application, maybe every week or every day. And then inference refers to where you're using the algorithm. So you're done training, now you're feeding, for example, an image in and you get a label out. And that's something that, again, depending on the application, can be done very often, so 1 billion times a day, for example. And of course, while a single inference run doesn't consume a lot of energy, that can add up to a lot of overall energy consumption. And Google and Facebook are both reporting that in terms of ML, most of the energy consumption for them is coming from the inference phase. So what we learned from this part is that the frequency of the different the activities across the different life cycle stages of a machine learning algorithm really plays a big role, and that's something we understand much more poorly than the energy needed per run. Okay, but what we're actually really interested in is the overall compute-related energy consumption of machine learning. And that one can also take a top-down perspective to understand that better. So what one sort of knows is that information and communication technologies account for around 1 to 2, roughly, % of global greenhouse gas emissions, which is in and itself a really uncertain number, so should be taken with care. And only a part of this is due to machine learning. And we don't know how large this fraction is. One can sort of constrain the number a little bit. It's likely not that large, but it would be great to have better data on that to really understand also not only what is the overall impact from machine learning, but also what are the dynamics, the underlying dynamics. So our data centers, historically have run more internet traffic, general data traffic, and simulations, for example, and now are shifting more and more towards machine learning. And is the growth attributable to machine learning or not? And these are questions that we currently cannot answer, unfortunately. And then, as I mentioned before, that energy consumption or those emissions actually come from operational emissions and from embodied emissions. And of course, we're not only computing in large data centers, we're also computing in distributed servers and smaller devices that have a relatively higher share of embodied emissions. Okay, so moving to the second part, let's look at the application impacts of machine learning. And Priya is going to talk about this in more detail, but I wanted to just briefly mention what machine learning can be used for in climate change mitigation and adaptation by just listing a couple of examples. So, for example, railway system operators like the Deutsche Bahn in Germany use predictive maintenance to increase the reliability and the cost competitiveness of their operations. So here, for example, they have sensors and switches and can then predict when a switch is about to fail, and therefore save a lot of money and make their operations more competitive. Then you can use machine learning to help with the development of new energy technologies such as batteries. It can be used to speed up the experimental processes to develop better batteries and better materials, for example. It's also used in climate change adaptation. This is an example of predicting locust outbreaks to prevent large-scale crop and harvest fails. And this is really important to secure food in vulnerable areas. And people also use machine learning in large simulations to speed up these simulations and make them much more computationally efficient. And this is an example where people are using AI to help design better urban areas, new urban areas, to understand the wind flow and the microclimate in this new districts that they're designing. And by being able to run many more configurations, they can much better design those new districts. So the impacts are summarized in this figure, and I'm not going to take too much away from Priya's talk, and but I just wanted to point you to that we have made a categorization of the kind of effects that machine learning can have, which is on the left. So these are different roles that machine learning can take, such as helping with forecasting, for example, or with system optimization and control. And then we map them to greenhouse gas emissions impacts on the right. So these improvements can help with better policy design, monitoring and enforcement. It can help with R&D for low carbon technologies. It can help with planning and design of relevant systems, such as markets or urban infrastructure. And it can actually help with operating engineering systems, such as heating and cooling systems. And what is indicated with the red bubble here is that, as I said, it's a multi-purpose technology, and that also means that it can help activities that counteract decarbonization, and that may lead to actually much larger emissions. So, for example, machine learning is used in oil and gas exploration. And actually it's used in oil and gas sectors like across the supply and across the value chain, and actually helps in many ways to make oil and gas cheaper, and potentially decreases the ability to shift away from fossil fuels. It's also being used, for example, in large-scale cattle farming, which is associated with a lot of emissions. So these are just some ways that can be used to counteract decarbonization. And I wanted to dive deeper into one example here that also shows how difficult it is to estimate the impacts that come from machine learning and the difference that machine learning makes in those applications and processes. So it can help actually with creating efficiency improvements in crude oil refining. So crude oil generally is turned into lighter hydrocarbons by heat from coker units. And you need to accurately predict coke buildup in pipes. And machine learning can actually help here with those predictions. And then it enables to maintain the equipment better and reduce ultimately also the energy consumption in the refining process. So essentially with this, machine learning is helping to reduce emissions in the refinery. But at the same time, of course, it's also reducing costs and reducing costs for oil products. So we need to think about how the application ultimately affects the emissions from the whole energy and economic system, because the reduced cost of oil products, of course, may actually increase the use of them or make it more difficult to shift away from these oil products. And that effect is sort of what we mean by this last area, the system level impacts. And I wanted to walk you through some examples, what we mean with the system level impacts. So the first one is the so-called rebound effect. And here you have the effect that reducing the energy consumption often reduces costs, and that money that's being saved is being used again and is often used in a way that causes more emissions. So that eats up the efficiency gains and sometimes can also even result in overall more emissions. And certainly in our coke buildup example from the refinery right now, it's likely that some rebound effects will also play a role here. And it is also generally true for efficiency gains with machine learning when systems are being optimized. Then there are things like lock-in or path dependency effects. And here we're talking about effects that happen when technologies compete and start dominating markets. And often you have the effect that you're locking the society into a technology, and sometimes the suboptimal technology early on that actually may also hamper decarbonization. And an example that relates to machine learning here is machine learning's role in autonomous driving. So essentially, autonomous vehicles are not possible without machine learning. And this technology reduces the barrier to individualized transport. So it reduces the barrier to driving. And people are seriously worried that it will increase individualized transport and actually take away from public transportation in that way. Also, again, our coke buildup example has the danger to lock us into carbon-intensive fuel sources. Then machine learning can also change consumer behavior. So it is widely used in advertising, and trends in advertising may change the consumption patterns. And therefore, that may also lead to increased emissions through the emissions embodied in those products that are being consumed. And of course, also, again, touching the role of machine learning in use in social media and online, it also has effects on communication and education. And machine learning algorithms can actually lead to increased polarization online. And therefore, there's also the danger to increase opposition to climate policies. And they can also result in a spread of misinformation and amplifying controversy. So there's really a danger to actually risk opposition to climate policy through the echo chambers that machine learning can create online. So that was a super quick tour over system level impacts that machine learning could potentially have. We turned this framework that I illustrated in this way here in this talk. We actually showed it a bit differently in the paper. So this figure here contains a lot more information. And what we also show here by these arrows coming down, going in and going out, is that there are criteria that, I mean, we're trading off sort of the precision in which way we can estimate the greenhouse gas emissions and the scope that the machine learning application has. So starting with the computing related impacts in this part A, here we have a very small scope. So we're constrained to a fraction of all information and communication technology emissions. But we can estimate those emissions quite well already. Then if we look at immediate application impacts, this is an area that already affects a number of different sectors, such as agriculture, power systems, buildings, and so on. So the scope is much larger. We're still able to estimate the emissions for some of them, not so well for others. And then the system level impacts have potentially very large scope, but they're very difficult to quantify and to understand what's happening here. So this is really how one has to think about measuring these different effects. So to conclude, I wanted to address a little bit on what we already know about how to measure them, and also what can be done from a policy perspective to address those impacts. So starting with the computing related impacts, it's currently very possible to measure the footprints of individual operations or individual algorithms with online tools. There are a lot being built right now and also integrated in larger frameworks. And they also allow developers to reduce the impact by choosing more efficient models and also reducing wasteful model retraining and execution. Of course, there's a lot more information needed on the machine learning use patterns and practice, because we still don't understand the overall impact of machine learning, and we want to monitor better the industry trends. So related to this, we want an assessment of the total compute load in data centers that can be attributed to machine learning. And ideally, we want to understand also how that is distributed between the different model life stages. So some policy approaches that can be taken here. So first of all, policy can, of course, help with gathering this information from especially data centers. There's a lot of discussion about increasing transparency also on the level of individual AI applications. That is a much more tricky thing to implement, and would be also unclear how much actually would be gained by having these large-scale databases of almost every application of AI that is being conducted. Then certainly an approach that would be very helpful is better, more carbon pricing of electricity. If you make compute much more expensive, of course, there are a lot more incentives to actually increase energy efficiency. So in terms of the immediate application impacts, it's necessary to start more and more quantifying and evaluating also the impacts where possible. And depending on the application, this might be actually quite feasible for energy efficiency applications, but might be much harder for other applications such as, battery development, for example. And there's certainly still methods, and Felix already mentioned life cycle assessment. There's still methods missing here to really understand what's the marginal and the counterfactual benefit of machine learning, especially in established processes. Then a fine-grained taxonomy of machine learning systems might actually help here to develop these kind of approaches. And ultimately, what we want to get to is having better assessments of area or sector-wide impacts from those case studies. So we want to aggregate and understand better, how much is actually the potential impact of machine learning-driven technologies, let's say in buildings. And to shape these impacts, a big lever is to foster work on climate relevant applications of machine learning. And here policy can play a big role again. So policymakers can support interdisciplinary machine learning research and the deployment on these climate relevant applications. For example, through funding programs, through pilots and test beds, which are really important for deployment, infrastructure, and helping people to work in climate relevant areas, so workforce shifts. And then we also need general standards and best practices to help stakeholders assess the cost and the benefits of new machine learning projects a priori. That's really why we do all of these exercises, to help people decide better what is actually the climate impact of these kind of projects a priori. And then on the system level, it's really important to consider the climate effects of all machine learning applications. So for example, recommender systems don't actually have like a connection to sustainability immediately, but they may have actually a large impact on sustainability. So really bringing in this climate considerations into all kinds of machine learning applications is important. And then we'd like to account for machine learning and digitalization and forecasting and scenario analysis in the machine decarbonization models, for example. So here, digitalization still isn't systematically included in such large-scale models, and machine learning is sort of basing on digitalization. So you need to start both with digital technologies, but then also think through the effects of machine learning and how to display them in decarbonization pathways. And here's some ideas: is that machine learning may affect efficiency, production and consumption rates, learning rates of technologies, resource constraints, financial assumptions, and so on. So it has potentially effects on many of the assumptions that are made in such models. And in terms of policy, this is a rather vague recommendation, but is to bring in this climate thought into technology assessment of machine learning and AI, because often machine learning and AI are not viewed in the climate relevant lens or energy relevant lens. And this is really important throughout all machine learning technologies. So together with colleagues from Climate Change AI and the Center of AI and Climate, we wrote a report for the Global Partnership on AI, discussing many of these policy approaches in more detail as well. So this is a pointer here to this resource for those who are interested. Yeah, and I'm happy to take any questions now. I'm going to stop sharing. Sorry to go over time a little bit.
No, that's not a problem at all. Any questions?
Okay, so Lynn, I have one question on your previous slides on the simulation part, because you mentioned that you and your authors works on the AI analysis on the climate change, especially to do those simulations or the computations of the air circulation within the city, doing those models, right? So I remember that there could be some like existing computational models that can, based on like physical or whatever, those existing knowledge to work on that. I'm just curious about what is the interaction between the newly emerged AI algorithms and the existing like computational models. So are you integrating these two together, or you based on your exploration, which one works better than the other? So yeah, that's my question.
Yeah, so I mean, this was an example that I mentioned, but it's not something that I personally worked on. So this was an example from the Austrian Institute of Technology. Mm-hmm. But you're pointing at a really important work going on in the machine learning communities, is connecting physical models with machine learning. And there are various different ways that these can be integrated. So sometimes machine learning is just providing sort of input parameters to these models. Sometimes machine learning is like playing a role for certain small aspects of the model. In this example, the machine learning algorithm approximated the whole model by learning essentially from the input configurations to the output, learning the map, learning sort of the function that the model displays, and that can reduce computational time from hours to split seconds. because it's just a much smaller representation of the model, and essentially the whole computations don't need to happen. So that's something that's also being done in, for example, climate science, to speed up simulations there. Climate science is especially benefiting from this because this machine learning allows them to have much more localized predictions, for example, of climate effects. So I personally don't work on this, but I would defer those questions also to Priya, because she does work on integrating physical models with machine learning.
Yeah, because based on my experience, I work on some like machine learning algorithms on like calibrating the simulation model or physical computational models based on some experimental data. So I know that in the statistical field, there are some basic approaches such that to calibrate or quantify the uncertainty of your computational model, your observational noise, and also the model discrepancy. So those are already well established since like 1990 or something. So yeah, I'm just curious about like, because you mentioned something like AI neural networks, and I'm curious about like whether there will be any advances in that field, like utilizing the AI thing, because sometimes the AI is kind of a black box and it seldom provides a certain quantification. So I'm not sure that if there is any ongoing work in this field. So yeah, that's why I asked this question.
Yeah, also for uncertainty quantification, that's another like cutting edge area sort of where machine learning is going towards. Yeah. Maybe Priya wants to jump in directly. I don't know.
No, happy to defer to after my talk.
Yeah, okay, yeah, Priya, I'll hold the question for you then. Again, for you. Okay, thank you both.
Any other questions? Otherwise, I do have a question. Okay, it seems others don't. So Lynn, the system level impacts that you are talking about, it seems everything is going towards a negative. Is that sort of a bleak assumption?
So everything is going towards what?
Towards the negative. It seems like we're losing on the transaction.
Yeah, I mean, I was thinking the same, like all the examples that we have are sort of increasing emissions, but I mean, there are also positive effects, assumable. For example, in communication and education, I mean, you can perceive that much more information on both what's happening in climate change, but also maybe how to mitigate can be helpful. And people even discuss nudging or, targeted influencing of people online to nudge them in the direction of thinking more about climate change, which is another tricky area, sort of, but people are even thinking about that. Of course, you can also have consumer behavior shifting towards more environmentally friendly products. The thing behind that is that you always want to increase sales, right, with targeted advertising. And generally more consumption results in more emissions. But if you're able to shift consumption to such as used products, for example, or more low carbon products, that could be a way to do that. I assume that also in the transportation sector, there are ways that systemic effects can actually help. Yeah, but it's true that the examples are listed are all negative.
Do you mind if I jump in too, Lynn, with a perspective?
Yeah, sure.
Yeah, I mean, I think like tying together also what Felix and Lynn were talking about, I think it underscores the extent to which there is sort of a deep tie between the policy problems here and the technology problems. Today, a lot of AI and machine learning technologies are implemented in a scenario where there isn't incentivization for something to be aligned with climate change, right? So if you implement AI to foster the development of autonomous vehicles, there are ways in which this can be actually a climate beneficial thing, right? If you have whatever autonomous people movers that are connecting people between public transportation and their end use, and you're kind of fostering the use of public transportation. But absent macro level incentives to make that happen, of course, you'd sort of expect that since climate change is external to many different markets and the ways that we think about actually progressing profits and progressing society, that's sort of why you see the emergent applications, I think, going that way. Whereas I think in a world with a lot of really strong climate incentives, I think we would start to see much more at the forefront, potentially very positive examples there as well.
So it all comes down to policy, it seems like.
A little bit the message is trying to
but also,
yeah.
I mean, policy is important, but also, I mean, I think there are lots of choices that those who are developing technologies can make also at the more micro level, right? So even things like companies that set internal carbon prices, that's not waiting on the entirety of public policy to shift, but it does affect that development within that particular company, and it's a scale at which it is potentially easier to affect change as an individual working at a company. Or you have the ability to think about when you're actually doing research, right, which is in some sense slightly away from application, think about, hey, am I going to think about the problems that, you know, foster public autonomous transportation or private autonomous transportation, because those problems look subtly different. So we also can, in our research, make various kinds of choices that sort of nudge the deployment in different directions as well.
But that being said, oh, sorry, you have another question?
Actually, that was interesting because I don't want to make this the round table because we have
yeah, that's true.
But one of the points is like we as researchers, should we opt for less number of parameters in our machine learning models? Is that the solution for us? Like,
I mean, that really depends on the task that you're trying to solve, right? Sometimes it's really important to drive accuracy up, right? If you can save lives in, let's say, medical applications by having more accurate models, and you consume such and such more energy to develop that model, maybe it's worth it. So I think really, I mean, it's a trade-off. But at least we now have tools to sort of also understand the trade-off better. And that being said, in not all cases, less parameters mean worse performance. So people are trying to develop more efficient models with sort of retaining performance or just having small degradation of performance.
mm-hmm. I think there's a question online as well from Naomi. Have you ever made a presentation to the finance industry? I'm sure that investors and shareholders who focus on ESG and sustainability would like to know more about sustainable AI activities.
Yeah, so I think both Priya and I get quite some interest also from industry, either like companies or larger roundtables. There's only so much single people can do, I think, in terms of giving presentations. But yeah, there's certainly a group of stakeholders that is interested in this area.
Okay, perfect.